hopefully everybody, sorry about that. Okay. Hopefully everybody here knows what the answer to this question is. I mean, after all, we are at Starknet Hacker House, so. But for those who don't, the definition for us is zero knowledge is slow, expensive, and hard to use. As of now, the ecosystem is mature, and there's quite a bit of ZK languages out there that are also growing. Take Nor, Leo, Maiden, and of course our favorite, Cairo. But there are still some core issues that we personally see as developers and engineers in the space. And that's high cost in ZK, that's unclear tool chains, that's super RAM intensive execution that even takes more than Telegram. And I know we're all using that right now because we're in EthDenver. So, but in the space, in the realm of ZK, there is still a use case that a lot of people see fit. Some would say a prodigy. And so this use case in particular is something that Vitalik believes and argues is perhaps the future of ZK and ML. And that is ZKML. But, excuse my language, it is a pain in the ass right now to do ZKML. And that is because ZK is massive. And if you think about ML, it's glorified linear regression, which is also massive in computation and proof size, and size. And so we've been talking with projects in the ecosystem, lead faces such as Gizatech as well, who also face these limitations and boundaries. And so the issue right now is that ZK simply can't support large-scale computations. So STARKScale tries to aim to solve all these aforementioned problems. We are building an infrastructure to turn single-threaded Cairo into a multi-process parallel process. And so think CPU to GPU, how we turn computation to parallelized in that sense. We're trying to turn single-threaded Cairo into multi-threaded systems or multi-threaded processes. And so we hope to decrease proof size, increase the speed, and also just enable more ZK scalability. And so simply put, how do we do this? Well, STARKScale is a ZK distributed system. And so we split our architecture into three folds. First off, we have the first implementation, which is ZK Hadoop, which is the first algorithm that we're trying to parallelize. But that's our MVP for now. Secondly is the distributed system. And thirdly, it's a recursive verifier to make sure that although we distribute and execute different Cairo programs all at the same time, it still compiles down to one proof. And so we'd love to dive deeper into it later, but this is the repo that we made for this hackathon. As of our journey, we built fast. We were the first team out of the Starknet Fellowship. Thank you, Mehmet, who we know is stuck in visa issues right now. We also won the last Starkware Hackathon, and recently we actually rejoined Stanford Blockchain Accelerator as their cohort portfolio companies. And so now Felix and I are here at EthDenver, just building out more of the MVP and also asking for help from the mentors because this technology is so difficult. Of course, this is quite a hefty task, and so in a couple days we weren't able to finish everything, but it was really great to get all the help from the mentors and also see where we move next. And the team's excited to say that we really want to continue forward. And so we're going to continue our current conversations actually with potential customers like Gizatech and also Hele to see where our infrastructure can kind of fit into their needs on how to scale ZK. So why now? After all, we think that Starknet is an amazing ecosystem and also the mentors in general. But the thing is, we truly believe that Cairo is mature and one of the top ecosystem tools right now. And so we aim to kind of accelerate that and also do it alongside mentors who actually want to help us and actually care. My name is Tommy, and this is Felix, and we're a team coming from alumni and uni students from Berkeley and Stanford. We'd love to talk more about it, so please contact us when you can. But for the meantime, I'd love to pass it off to Felix, who's our technical wizard, and also the mastermind behind all of this implementation.
Hi everyone, I'm Felix, and I just want to stress that we have learned so much during the hackathon, and we're really thankful for all the mentors and event organizers. So before coming to here, we're not even sure how the end-to-end proof for Cairo 0 or Cairo 1 works. And now we're able to make sure that the proof generation for Cairo 0 and Cairo 1 both works. And we also learned about Cairo 0's building and hint function, and we also be able to build a recursive verifier using Cairo 0. In addition, we got a lot of business aspect hints from a variety of mentors, and this really helps us a lot. So we of course go through a fast technical annex, and then because there's a lot of technology involved, so I first go through a brief overview, and then people can question and ask me in person later about what we're doing. So first, we're basically just a map reduce system, but we're adding the pattern prover or stone prover and the verifier into a worker or mapper node and reducer nodes. The mapper node will be the one who's aggregating all the results, and then the mapper node will be the one who's partitioning all the data, and the reducer node will be the one who's aggregating. So this is how we built during the hackathon, an end-to-end ZK map reduce system. So each mapper node will have a Cairo VM, and each will have a stone prover, and each of the reducer node will have a lambda verifier and a lambda prover. Yes. And then in addition to that, we also build a recursive verifier because we want to make sure horizontal scalability actually works. If we don't have a recursive verifier, we have like 10 proof for 10 nodes. And recursive verifier, in this case, we can combine proof and compress it into one. So this is like inspired by Sharp, so we can kind of build like a local Sharp system using Carol 0 verifier. So there'll be a mapper program 1 and mapper program 2, and then they'll both get the mapper 1 proof and mapper 2 proof from the stone prover. And then we'll verify this using a Carol 0 verifier. And then the Carol 0 verifier will have a trace of it verifying mapper 1 and mapper 2 proof. So after we prove the execution of verifying Carol 0, we can make sure that we can get one proof that proves that we verified mapper 1 and mapper 2's program. So this is the final architecture that we want to build, but we don't have time yet. It's basically we got everything done, but we haven't connected the components yet. Yes. And in the future, because we are doing distributed system, and this is currently just one node, we want to, of course, like deploy it on Amazon and then have multiple nodes to actually make data parallelization and and computation parallelization possible. So in the future, users just have to send the data, and then they'll just go through all this, and they'll get a proof and output that they envision. So we kind of allows like non-technical user or like people who's not that familiar with ZK and distributed system can use our framework and then get the goal they want. So that's basically our presentation. Thank you.
So I have two questions. The first one is, what was built during the hackathon, and what have you done in the 4 days?
Yeah, so basically we also participated in the winter hackathon and we won over it. And previously, in the winter hackathon, we don't have any of the stone prover and the verifier yet. We only just use code Carol functions and then just do the computation and make sure we got the correct result. And now we build an end-to-end product that we actually have all the stone prover, the lambda prover and the lambda verifier incorporated in all of the modes, so that we can actually prove and verify all of the process. And in addition, we have built a recursive verifier that we haven't been able to manage before, and then we kind of incorporated with verifying Carol 0. And in addition, we realized that recursive verifier only works for Carol 0, so we wrote a program in Carol 0 in this hackathon. So we can basically learn Carol 0 in a day, and then we wrote the mapper function and reducer function in Carol 0, and then put it into a stone prover, and we also learned about how to use the config files to set up the FRI list, and learn about the folding scheme, and then the query and folding scheme. And then we put it in the verifier in Carol 0, and we successfully got the thing to work.
Okay, and so second question about MapReduce. So the way I understand it, you split the computation into different segments and recombine them. So yes. How is it different from continuation in the ReZero, Premiere, or other?
Yes, because like the process of generating like proof, you have to go through like the program that together compile the chasm file, and you get a trace memory and private input and public input. And what we're doing is that, and then usually to get a proof, you first go through the execution trace. You get the execution trace first, and you put it in the stone prover, and then you get the actual proof. But we are first parallelizing the Cairo code first. So we're making Cairo code multi-process, which is like what people haven't done before. And for continuation, we also, for the generating proof part, we're also actively looking for improvement for like the compression scheme. So we're also looking at like FRI plus snark and different like mechanisms. We're really open to learn about how to make the proof compression and the proof generation faster. So we're pairing on two sides, one on the proof generation side and one on the running the zero knowledge language side.
Just one comment also. You said that you learned about the hint on Cairo 0. Hint are now also available in Cairo 1, so you can also make hints in Cairo 1.
Got it, thanks a lot.
It's a work by Raylab. It's called Cairo Hint. You can find it on GitHub.
Oh, that's very good.
What do you see as the biggest limitation in terms of like computing resources do you need on AWS, or what kind of do you see as the biggest bottleneck?
Like I think the current, yes, I think AWS is definitely one, because everything currently we're running one node, so we can't really like leverage the power of distributed system. So we kind of want to, in the next time, we kind of want to combine it with like AWS EC2 instance, and also combine it to like the Lambda functions, so that we can actually run a demo of it and show that the scalability and then the data parallelism technique actually works. Because currently, like when we try to learn Lambda works, there will be like memory constraints. So if we get too much data or the file is too big, it simply just breaks. And we believe that memory parallelism, like splitting the memory, can actually make this possible. Because we have small solid smaller trace when we're generating the zero knowledge language.
Another limitation is that we want to build this system for Cairo 1. And so right now we need a Cairo 1 verifier in Cairo 1 to do a recursive prover, or verifier instead.
Yes.
There is one.
Here goes.
Yes.
It takes in.
Oh yeah, we talked to Marcel before. I think the problem for that is that currently like the cargo run when you generate doesn't work with Spark. So you have to use cargo run, and everything you need everything written in a single file for it to get a computation trace. So that's one limitation. Yeah.
Something you do a complaint list and we work on it.
Sorry.
I think we need it. Any complaint list is welcome.
But we really enjoy learning about the tech stack, and then it's like a super fun experience. Yeah.
And so maybe last question on my end is, so obviously this is a very ambitious project. You guys, I guess, are looking to create a company out of this. What's the end game? What's the vision? How do you see this happening?
Our vision is have two things, because currently everyone can kind of agree that like zero knowledge for developers is still in like the early stage, and we kind of want to make it into like SDK for like ZK Spark system or like ZK Hadoop system, where people can just utilize our framework and do something like in Python and call SDK, and then we'll do everything for them. So that's the first thing. And the second thing is that we think that we can, since ZK is like a mature, it's like a super fast growing language. We believe that ZK lang will be like, there'll be a lot of use case, and then there'll be a lot of like use case for like heavy ZK computation. And we're basically parallelizing ZK computation. So we kind of want to serve ourselves like a GPU for like, not really a GPU, but kind of like a GPU for multi-process zero knowledge language. Yeah.
Another point to add in is in our long-term vision, we also aim to be sort of surfacing as a B2B, like infrastructure as a service company, where we could implement this case, like you said, for different protocols that need to scale their ZK computation. And also, just taking into account, there are also, I guess, pathways for, let's say, integrating other ZK languages if we see fit, and also building out the full distribution and decentralizing nodes in the future for worker and networks.
And like MapReduce is our first MVP, because there are a lot of other distributed system use cases that we can test on, and many other like proof compression techniques we can work on. So we think this is like a very big opportunity and big like space to try and learn. Yes.
So I just made that comment. I guess obviously this is very ambitious and very, very cool, no doubt. I have a hard time seeing the business model because you are leveraging the infrastructure of others, which also will optimize and go toward that path and make the competition a bit complex. I would say that you doing it is actually very good for yourself, for us to create a name for yourself and to get the knowledge to actually find where there is a good business. But like, this is very impressive.
Thank you.